Hello and Assalamu alaikum students. This is part 2 of our work energy and power lecture. We are going to cover following topics: potential energy, work done and potential energy. Under this we will dissect following two systems, which are tomato earth system and spring mass system. Then I will give you a quick introduction of conservative forces, then an important topic which is conservation of mechanical energy. After that, we will study work done by external forces, under which we will investigate external forces and internal energy transfers. And at the end, I will give you a brief introduction about power and lastly, efficiency of machines. Let's do a recap of definitions of work, energy, and power first. The work is refer to an activity that involves a force and movement in the direction of the force, while energy is the capacity of doing work. So you must have an energy to accomplish work. It is like the currency for performing work. Like we have notes or currency to buy something for shopping, and similarly energy is the currency for performing work. The more you have, the more work you can do. And power is the rate of doing work or the rate of using energy, which are numerically the same. Okay, potential energy. It is the energy which is held by an object because of its position relative to other objects or stresses within itself because of its electric charge or other factors. So which means that the value of potential energy is relative with respect to a reference. And there are three types of potential energies, which are gravitational, elastic, and electric potential energies. So the gravitational potential energy is actually the energy stored in a body due to its position in the gravitational field. And here we consider gravitational field because of Earth only. It can be because of any object, because any massive object has a gravitational field around it, but the most prominent one is the gravitational field because of Earth. So we are taking only the gravitational field because of Earth into consideration, and its formula is Pe, means potential energy, the small g mentions gravitational potential energy, equals to mgh, and here h is the height of the object from a reference point in the gravitational field. And then second is elastic potential energy, which is the energy stored as a result of applying force on an object to deform it, like for example by pulling or twisting a flexible object. Okay, its formula is P dot E, stands for potential energy underscore elastic, to differentiate it from the other type of potential energies. It is equal to 1 over 2 kx square. It resembles the formula for kinetic energy also. So keep the two differences in your mind. So 1 over 2 kx square, here k is actually called as the spring constant, and x is the position of that object with respect to a reference position or its normal position before twisting or attempt to deform it. And third is electric potential energy. This is the energy which is stored in a charged particle by moving it against the electric field. However, the details of electric potential energy are beyond the scope of this lecture. Okay, now you know the definition of potential energy, and you have the concept of negative work done, and you also understand the system of masses. Here we are considering an isolated system, which means we are ignoring everything and every outside influence on this system. The isolated system is tomato earth system, which means in this system we ignore everything other than a tomato and earth. The earth exerts a gravitational pull on the tomato, and tomato has a potential energy because of its position in the earth's gravitational field. Let us consider a boy throws this tomato upwards. We are ignoring the boy and the force he used to throw this tomato upwards, and only consider the gravitational force acting on the tomato. So how much work is done by the gravitational force while the tomato goes upward? It must be equal to the weight of the tomato times the height it attains. We call it Wg. Since the weight and height of since the weight of the tomato and the height it attains both are in opposite direction, the work done will be negative. Means the work done by the gravitational force while the tomato is going in upward direction is negative. So it is represented with minus Wg. Okay, now the tomato reaches its maximum height and starts to fall down. Now the direction of its motion and the gravitational force both are in same direction. Therefore the work done will be positive and it will have the same magnitude as before. So it will be represented as plus Wg. The negative and positive works here can be explained in terms of addition and removing of kinetic energy to and from the system. So the negative work done by the gravitational force on the tomato means it can be looked at like the transfer of energy from kinetic energy of the tomato earth system, and this transfer of energy from the kinetic energy is actually transferred to the potential energy of the system, means that the kinetic energy is removed and potential energy is increased by the same amount. Okay, so for either rise or fall, the change in potential energy in the gravitational potential energy, this delta PE means that change in potential energy. It is defined as the negative of the work done by the tomato in the gravitational force, because when the tomato is going in upward direction, the work done is negative, means but the potential energy is increasing, right? So it is opposite to the work done. Potential energy is being added and work done is negative, while when the tomato is coming downwards or it is falling, the work done is positive but potential energy is decreasing, so opposite again. That is why the change in the potential energy is negative of the work done. Listen again. When the tomato is going in upward direction, the work done is negative but the potential energy is increasing, means that the change in potential energy is positive. But when the tomato falls down, then the work done is positive but potential energy is decreasing, means that the change in potential energy is negative. Okay, so in both cases, either whether it be rising or while the rising of the tomato or falling of the tomato, the change in potential energy and the sign of work done are opposite in nature. That is why the change in potential energy can be considered as negative of the work done by the gravitational potential energy on work done negative of the work done by the gravitational force on the tomato. Now we consider another isolated system, which is spring mass system. In this system, we will consider elastic potential energy and study the work done during expansion and compression of the spring in the same way we did in tomato earth system. Here x is equal to 0 is the normal position of the object. Now we compress the spring against its spring force, which tries to keep it in the normal position. Therefore, the work done by the spring force will be negative because the direction of the object is against the direction of the spring force. During this compression, the kinetic energy has decreased and more potential energy is stored in the system, which will be released once we let it go. Therefore, we can say that the spring force the spring force has removed the kinetic energy from the system and added to its elastic potential energy. Therefore, the change in kinetic energy is negative and change in elastic potential energy is positive during the compression of the spring. Now we let it go. In this case, the object is released to go back to its normal position under the action of spring force, and during this object's motion towards x is equal to 0, the spring force and motion of the object both are in the same direction. Therefore, the work done is positive. Also, its kinetic energy increases because it speeds up, and its potential energy decreases because the spring expands. Now, therefore, the change in kinetic energy is positive and the change in elastic potential energy is negative during this expansion. Therefore, we can say that the spring force has added to the kinetic energy of the system. And in a similar way as before, we can write the equation that change in elastic potential energy is negative of the work done by the spring force. Okay, now a quick introduction of conservative forces. So the conservative forces are the forces by which the work done on a particle moving around any closed path does not depend on the path taken, and the work done during the closed path is equal to around any closed path is equal to 0. So the work done by a conservative force on a particle moving between 2 points does not depend on the path taken. So these are the two conditions for a conservative force. First thing is that the work done by a conservative force on a particle moving between 2 points does not depend on the path taken, means it is independent of the path. And second is the net work done by a conservative force on a particle moving around a closed path is 0. Like there are 2 points, point A and point B, and there are 2 paths which are leading an object from point A to point B. There is path number 1 and path number 2. So path number A, if we follow path number A to move the object from point A to point B, the work done will be like, let us say, WAB1, okay, and the work done in taking the object from point A to point B via path 2, that will be WA to B2. So both of these work done will be equal in magnitude, okay. And for the second condition, the work done in moving the object around the closed path means bringing it from A to B and then from B to A back, the net work done will be equal to 0. And here we can write that the work done along the path A is equal to work done along the path 2, like this, okay. And the work done from A to B and back to A will be equal to 0. And the forces that we have studied just before this, the gravitational force and the spring force, both are examples of conservative forces. Okay, now a very important topic in physics, this is a law, that conservation of energy, or we also call it law of conservation of energy. It states that the total energy of a system remains conserved or does not change. It can change only by the amounts of energies that are transferred to or from the system. So the total energy remains the same. The energies can be transformed from one form to another but cannot be created or destroyed. The total amount remains the same. It is mathematically it is represented as delta. W is the work. Actually, we can consider work equivalent to energy also. The change in work is equivalent to change in energy. So the work done, the change in work is equal to change in total energy is equal to the total change in mechanical energy plus total change in internal energy, the thermal energy, and the total change in other forms of internal energies. So this law of conservation energy is not something which is derived from basic principles, but it is based on countless experiments, and scientists and engineers have never found an exception of it. It always exists in all sorts of systems. And here this mechanical energy, E with subscript of MEC, is mechanical energy. Actually, this mechanical energy is equal to the sum of kinetic energy and potential energy of a system. Now we take a look at conservation of mechanical energy, because the conservation of energy itself has a wider scope. It can include thermal energies and other internal energies also, but when we talk about mechanical energy, we are only dealing with kinetic and potential energies. So the total energy of an isolated system cannot change. It can only be transformed from kinetic energy into potential energy and from potential energy into kinetic energy, but the total mechanical energy remains constant. It is represented like this also, that kinetic energy, initial kinetic energy plus initial potential energy is equal to the sum of in final kinetic energy and final potential energy. This initial and final are with respect to change in the position. For example, like if in the previous example, the tomato earth system, the initial position can be the starting point of the tomato, and the final position and the final condition is when it reaches to its maximum height. So kinetic energy initial can be on the lower position and the potential energy initial on the lower position, and final kinetic and final potential energies are at its peak position. Okay, so since we are considering this as isolated system, it is considered isolated from the environment, therefore no energy transfers to or from it can take place. So when we talk about some principles and some laws, we confine ourselves, we apply some constraints and limitations under which that law exists. Okay, now let us see this example. This object, this ball, is at position A at a height h from the ground level. At this stage, at this height, the kinetic energy is 0 because it is not moving. So if when an object is in stationary position or it is not moving, the kinetic energy is 0. And at this height h, its potential energy at position A is mgh. M is mass, G is gravitational acceleration, and h is the height. And at this stage, this is the maximum potential energy and 0 kinetic energy. These two bars, these two scales are showing potential and kinetic energy. So when it starts to move down at point B, which is the middle of the height, the kinetic energy is 1 over 2 mv square. M is the mass and v is the velocity at this point, while the potential energy at point B will be equal to mg h over 2, because this is the height at which the ball is at this point. The potential energy and kinetic energy both will have equal magnitude here, and the total energy will be equal to kinetic energy at point B plus potential energy at point B. Now it continues to fall down until it reaches on the floor where the height is equal to 0, and we call this point C. So the kinetic energy at point C is equal to half mv square as before, and the potential energy at this point C is 0 because mgh and h is 0. Therefore the potential energy at stage or at point C will be equal to 0. There is no potential energy and maximum kinetic energy, because just before the ball strikes the ground it has attained its maximum velocity, and the total mechanical energy at this point will be equal to the kinetic energy at point C plus potential energy at point C. And at all these three stages, the energy at point A will be equal to the total mechanical energy at point B will be equal to total energy at point C, and we can call it the total energy E. So you must have observed that during the motion there was fluctuation in the potential energy and the kinetic energy. When the object was falling down, the potential energy was decreasing while the kinetic energy was increasing, but the overall sum remained constant. This is the conservation of mechanical energy. Okay, now consider another example in which we will see the conservation of mechanical energy. So we consider a 1 kilogram object sliding down a frictionless rail. So since we consider isolated systems, we do not consider any surrounding environment influence on it. So here we are considering an object of 1 kilogram mass sliding down a frictionless rail. Just like you can consider that this is a car on a roller coaster, and there is no friction between the tires and the rail, so it is frictionless, so that we could ignore the influence of friction on the motion. So at this stage it is at the maximum height, and it has certain velocity, and it is at maximum height 10 meters, let's say, and this is the position number 1, and it moves downward. Its velocity increases because it is moving downwards under the effect of gravitational potential energy, under the influence of gravitational pull. And at point 2 it has this kinetic energy, it is increasing, but since it was moving downwards, it was losing its height downwards. That's why it was losing its potential energy, but its kinetic energy is increasing. But when it again goes upward, it has a height lower than this. It has a height lower than point number 2. So see, it is still moving downwards. So when it is moving downwards, it has larger velocity, and means larger kinetic energy, and since it is losing height, it has smaller potential energy than before, and it keeps on going until it reaches at the floor with the maximum velocity. Okay, so at this stage it has maximum kinetic energy and minimum potential energy. So during this whole process at 1, 2, 3 and 4 point, the total energies can be represented like this. E1 is equal to sum of the total mechanical energy. E1 will be equal to kinetic energy plus potential energy at position 1. E2 is equal to kinetic energy plus potential energy at point 2, and E3 is equal to kinetic energy plus potential energy at point 3, and similar at point 4. And all of these potential energies and kinetic energies will be different at different stages at 1, 2, 3 and 4. The kinetic and potential energies will have different values, but their sum will remain equal. This is constant. So if the potential energy is decreasing, the kinetic energy will be increasing. If kinetic energy is decreasing, potential energy will be decreasing. So it makes the overall sum of the both energies equal to a constant value. So this is actually the conservation of mechanical energy. Now, after all this discussion, we are able to understand that the work is the energy transferred to or from a system by means of external force acting on that system. So positive work done on an arbitrary system means a transfer of energy to the system, and negative work means transfer of energy from the system. Means if the positive work is done, the energy is transferred to the system, and if the negative work is done on a system, the energy is transferred from the system. Okay, now external forces and internal energy transfers. So, an external force can change the kinetic energy or potential energy of an object without doing work on an object, means without transferring energy to the object. So, instead, the force is responsible for transfers of energy from one type to another inside the object. Okay, let us consider this example here. Initially, an initially stationary ice skater. The ice skater is in a stationary form. She is standing by a rail, and she pushes herself away from the rail, and then slides over the ice. Her kinetic energy increases because of the external force F on her from the rail. However, this force does not transfer any energy from the rail to her. Therefore, this force is doing no work on her. Rather, the work done is by or the kinetic energy increase is because of the result of internal transfers from the biochemical energy in her muscles actually. So those biochemical reactions have created energy, as a result of which they generated that force which increased the kinetic energy of this girl. Another example is this car. The engine increases the speed of the car with four-wheel drive. If this car is a four-wheel drive car, the engine will increase the speed of this car by moving them faster. So during this acceleration, the engine causes the tires to push backwards on the road. When the engine exerts force, the engine runs. The tires exert force to push forward. Okay, so this push produces frictional forces that act on each tire in the forward direction. The net external force F from the road, which is actually the sum of these frictional forces, actually accelerate the cars and increase its kinetic energy. But the F does not transfer energy from the road to the car. Therefore, it does no work on the car. Actually, the car's kinetic energy increase is the result of internal energy transfers from the energy stored in the fuel that has happened inside the engine of the car. Okay, and by simplifying the situation, we can relate this external force F, this one, with change in the mechanical energy of the object. So in the case of the ice skater, we assume that F is constant, which means acceleration is also constant, because F is equal to ma. If mass and F do not change, a also remains constant. When the velocity changes from 0 to v, it is the velocity 0 here and v here. The second thing that we assume is the ice skater is a particle and ignore any physiological and thermal changes inside the body. So we are assuming no physiological and thermal energy changes, they also remain constant. We assume that in that case the final kinetic energy minus initial kinetic energy will be equal to Fd cos of phi. This phi is the angle, this angle between the force and the horizontal. So this equation is derived from work energy principle, which states that the change in the kinetic energy is equal to the work done. Or we can write it like this: delta K, which is equal to Kf minus the final kinetic energy minus the initial kinetic energy, it is equal to Fd cos of phi. And if there is some height involved also, height means that the girl jumped, then there will be a change in potential energy also involved in it. Then total change in potential energy, this U actually here represent potential energy. So the change in potential energy plus change in kinetic energy will be equal to the work done, or we can write it like this as well. Okay, the power can be defined as the amount of energy transferred in a given time, and the average power due to the force, due to that certain force, can be represented like this: that if the amount of energy transferred is delta T during delta E during the time delta T, then average power will be equal to delta E divided by delta T, means the total transfer of energy during the total time. Okay, and the instantaneous power can be represented with this formula: dE divided by dt, means the transfer of energy during that particular instant of time. Okay. And the last thing now is the efficiency of machines. Efficiency of machine indicates how well its input energy is converted into its useful output energy, and it is a dimensionless quantity because it is a ratio between two similar dimension terms, and it can be calculated as follows. The general formula for efficiency is output divided by input times 100, and output can be in terms of energy or in terms of power. So we can write it like this also, that efficiency is equal to output power divided by input power times 100. So it is determined in terms of, or it is represented in terms of percentage, or we can also write it in terms of energy. So energy output divided by energy input times 100% is also the formula for efficiency of machines. That is all for today, and if you have any question, we can discuss during our next live session or on Kaizala. Thank you.